Hello, learners, and welcome to the final part about transition metals and coordination chemistry, which is crystal field theory. Like the beginning of every new part, I wanted to remind you of the pre-lectures and one-pagers and the previous information section. So, of course, you want to go to the pre-lecture area here. You want to make sure that you are completing the pre-lecture one-pager to orient your brain. And, of course, you also want to make sure you are reviewing concepts and completing practice problems for all the previous chapter information. So if you are having a hard time making those small connections with details, this is where you need to go back and do. So yes, it is extra work, but it's all about making sure you are completing the learning process if you really want to understand this material. Now, again, the goal of the lectures will be to enhance or add to pre-lecture information, but I also want to tell you that yes, it can be easy in this day and age to find a quick answer for most anything, but you must also consider giving yourself and your brain a chance to learn something new, meaning that you have to go through the journey of not getting it before you get the answer, right? So I will say, be okay with failing and getting back up and trying again, because that is a part of learning chemistry, and it will be worth it over time. The hard road is always going to become easy, and the easy road will always become hard. So let's get this final part started. America's next transition metal is on to another challenge. So far, in the last two parts, we have learned about transition metals and their properties, and went further to learn about how transition metals can bond with ligands to form complex ions with different geometry. Now, let's continue to imagine that transition models are going through another challenge called the Complex Ion Exploration Challenge, where the models must explore how complex ion bonds are formed, why certain geometries are preferred, and why these complex ions exhibit new properties like color and paramagnetism. And the transition models can only use two theories to make their explanations for our course, which are valence bond theory, which helps us explain basically bonding and geometry, and a new theory called the crystal field theory, which is all about understanding how d orbitals split in energy to create those new properties like color and paramagnetism. So as you can see here in this photo, we basically get a visual of what the crystal field theory is based on. So here we have these d orbitals, okay? And this is going to be part of a d orbital diagram, so we usually just write those little lines to help us. And we know that all these d orbitals are going to be basically the same energy, but we know that each orbital has a different shape, okay? So when ligands are going to be approaching these different shapes of these different orbitals, of course, the energy is going to increase. So we have our d orbitals here, and we see the energy kind of increasing. And this is the energy diagram, so we do see the arrow of energy going up here. And so again, when the ligands approach the different d orbitals, of course, that are part of the metal ion, because we are talking about a metal ion ligand bond, because we are talking about complex ions, just like we are from the last portion, right? We're adding another layer. So when those ligands are going to start approaching these d orbitals of different shapes, the energy of the orbitals are going to increase, as we see here. Energy increase, okay, folks? But we go further, right? Even though, yes, the energy is going to increase based on the shape of the d orbitals, and we have different shapes, some shaped d orbitals are going to have different energies than other shaped d orbitals. And so what happens is our d orbital energies are going to split. So we have two shapes that are going to be higher in energy and three shapes that are going to be a little bit lower in energy, okay, based on the octahedral complex ion that our course mainly focuses on. So, of course, there are different geometries you saw in the previous portion, but remember just to explain to you right now, for our portion, when we focus on crystal field theory, we're only going to be talking about octahedral complex ions mainly, okay? And this splitting of these d orbitals is what helps us understand complex ion properties like the color and paramagnetism, which we already talked about, is based on crystal field theory. And so we're going to basically get into learning all about this soon. So let's continue to make connections and get more understanding. So to begin our journey, we're going to use valence bond theory to create new hybrid orbitals that help us describe bonding and geometry in complex ions. That's what we're going to start with. But we need a new model called the crystal field theory to help us describe properties of complex ions like color and magnetism. So that's what we get into next, okay? As a bonus, once these new properties are unlocked, our transition models get makeovers, and we get to see some of them pretty much shine with different colors, okay? And finally, I just want to make sure that you're always looking out for those flashcard moments throughout the lecture. And that just means you want to stop and give yourself a chance to actively write down a concept on the front of the card, and an example, definition, or visual on the back of the card about what you just learned. So let's get into it.